Yeah, so today let's discuss shockwaves, and on Friday, Professor Harris is going to be giving a lecture, and Friday afternoon there are actually going to be two sessions. One session on, so we are going to be spending half an hour on review of quiz 2, but another half an hour we have a guest, Dr. Philip Spallard, and he is probably the world leading expert on turbulence and the turbulence modeling. So he's going to maybe spend a half an hour with us. And if you have any question about turbulence modeling, that's a good time. All right. Okay. So last lecture we looked at how do we go from the geometry of a flow, like a flow stream contracting, expanding, to how the pressure coefficient changes, right? So we have said, okay, for subsonic flows, as the stream contracts, the pressure coefficient decreases, right? You did the calculation on the board, okay? And upon the contraction of 1%, the pressure coefficient decreases by 0.02. That's for low subsonic flow, Mach number close to 0. And when you get to higher Mach number subsonic flows, the same contraction is going to drive more pressure coefficient change. All right, there is a divide by 1 over m, 1 minus m squared. Then when you get to supersonic flows, the relationship becomes the opposite. Upon the contraction of the flow, the pressure coefficient actually increases, not decreases, right? So that's what we discovered last time. And this time, let's actually put these, let's actually do a little bit of integration. So last time we did a differentiation, right, which is basically upon a small change, how does other stuff change? I mean, we have been doing differentiation for some time, and now let's actually do a little bit of integration and see how things upon large change, upon a large change in the Mach number, how does the pressure change? How does the temperature change? How does other stuff like density change? Okay. So first of all, what is Mach number? We actually only the ratio of your speed over the speed over. We never talked about sound in this aerodynamics yet, right? And in the future classes, if you keep studying, you actually go to study unsteady aerodynamics, and you are going to encounter sound over there. But we are not talking about sound yet. It's basically velocity divided by this thing gamma times p over rho. That we call it speed of sound. But it's we didn't derive this by deriving sound. We just derived this by itself, right? Okay. So let's say if I have a small change in the velocity, how does the relative change in Mach number relate to the relative change in velocity? If I have this big parenthesis, how do you figure that out? Okay, we studied what is the relationship of fractional derivative, fractional sensitivity of a ratio, right? We also studied the fractional sensitivity of a power, and in this case we have a power of half. Or power of minus half, if you think about this one divide as part of the power. We also looked at the fractional sensitivity of products, or basically you can write this whole thing as u to the power of 1. There is a constant. Let's just put the constant over here. Just let's not care about the constant. And p is going to be the power of minus half, and rho is going to be to the power of half, right? So that's how I can express Mach number in terms of product of powers. And we did look at how product and how power is going to translate into the world of fractional sensitivity. So can somebody help me write this out? 1 minus what? Half? Well, okay, so yeah, that's right. Let me do it slowly. I think I don't need to express it all the way in terms of du over u at one shot, right? So it's du over u, so that's from here. And now from the pressure is minus half of delta P over T, that's right? And for the density is plus half of delta rho over rho. And we know what is delta rho over rho in terms of delta U over U, right? What is it? It's the first thing we started in compressibility. It's minus square of the Mach number, right? So the first thing we studied in compressibility is d rho over rho is equal to minus m squared du over u. If I accelerate by 1%, the density would drop by m squared percent. Right? That's the first thing we learned. Then that translates into delta u over u. How about pressure? We learned the delta P over P in terms of delta rho over rho. That only works for isentropic expansion or compression. The relationship is gamma times, right? Do you remember like we were doing this a pressure volume diagram and adding heat at constant pressure, adding heat at constant volume, and then the isentropic expansion, we derived this, right? Okay, so now plug this in. Well, du rho over rho is minus m squared, so this is minus gamma m squared du over u, right? So plug this in, we get now plus 2 gamma m squared delta u over u, and then there is a delta u over u. So if you add it together, it'll be 1 plus gamma minus 1 over 2 m squared delta u over u. So this is basically the relationship between how a speed change relates to a Mach number change, right? So when Mach number is close to 0, 1% increase in velocity means 1% increase in Mach number. There is no surprise on that, right? Because speed of sound is pretty much constant. As you accelerate, density barely changes, pressure barely changes, therefore temperature rarely changes, therefore speed of sound barely changes, and the 1% increase is 1% increase. But at higher Mach number, the higher the Mach number is, the bigger change in Mach number is driven by the same increase in velocity, right? At Mach, so this is a gamma minus 1 is 0.4 over 2 is 0.2, so this number is 0.2. Okay, so if you are at Mach 10, this guy is 20, right? And this is 21, which means at Mach 10, 1% increase in velocity means almost 21% increase in Mach number. So the Mach number increases very fast as you are approaching vacuum. Well, I'm saying approaching vacuum because you are expanding. Remember, like in supersonic speed, a increase in velocity means expansion, right? I mean, like you're expanding into vacuum at Mach 10 at that speed. Okay, so this is the relationship we get. And now the first thing we want to we also know these relationships, right? So we cannot just write this in terms of delta u over u, but also delta rho over rho and delta p over p. So let's write them down. We know, for example, delta rho over rho is minus m squared times delta u over u. So delta u over u is minus 1 over m squared times delta rho over rho, right? And we can also write this in terms of delta p over p. I mean, this is now, this is product minus gamma, actually, I think the other way, minus gamma m squared delta p over p. Now we can integrate. Why? For example, let me just write the left-hand side also here. Okay. Now we can integrate because let's just flip this and write what is delta rho over rho. Delta rho over rho is equal to, we are multiplying both sides by minus m squared. So here, instead of delta m over m, I have actually m minus m times delta m. And underneath, I have 1 plus gamma minus 1 over 2 m squared. Right? Okay. And if I follow the math here, minus m times delta m is actually minus half of delta m squared. And I have 1 plus gamma minus 1 over 2 m squared. Right? Okay. And further, I can multiply and divide both sides by gamma minus 1. So what I get is delta half gamma minus 1 m squared. Well, and I can just plus 1 without changing the delta, right? Underneath, I also have, right? Okay, so that works. Now on both sides, I have a fractional derivative. One side is rho, the other side is 1 plus 0.2 m squared. And there is a ratio between them. Now let's translate that into our log-log plot. So if the fractional sensitivity of one thing is a constant multiple of the fractional sensitivity of another thing, what does that translate into a log-log plot? It's a straight line, exactly. A straight line in a log-log plot means what kind of relationship in a linear plot? No. So, you said that you gave two answers. Both are correct answers for something else. So, if I have a linear versus log plot, a straight line would be exponential. If I have a log versus linear plot, a straight line would be a logarithmic. But if I have a log versus log plot, a linear line is what? Just to recall the other day, we were looking at this relationship, right? P over P is equal to A. Linear is a constant function times delta rho over rho. And I don't like if you did the unified, you probably remember that translating to P is proportional to rho to the gamma power, right? Okay. Now we have a similar relationship. A linear plot in a log-log, a line in a log-log plot translating to a power law relationship. Okay. So for example, if I have a log x, log y, log x, if I have a slope of 2 in the log plot, then y is equal to x squared. Right? So a slope of 2 means as x increases by a factor of 10, y increases by a factor of 10, and another factor of 10. Y increases by 100, right? So that's power 2. If I have a slope of 3, that would be a power 3, right? So basically the slope is actually the power. So this relationship just means rho is going to be proportional to 1 plus gamma minus 1 over 2 m squared to the power of minus 1 over gamma minus 1. Okay? So let's think about what that means in isentropic expansion. As I increase in Mach number, my density drops, right? That's why there is a negative power in this. Okay? And this is a monotonic relationship. As I increase Mach number, increase further and further, density would drop all the way to 0. Right, and also And also, if you multiply density with that number, that's going to be a constant. So that also means rho times 1 plus gamma minus 1 over 2 m squared to the positive power gamma minus 1. That is going to be proportional to a constant 1, right? Proportional to a constant means this number wouldn't change upon isentropic expansion or compression. That's called the total density or stagnation density. Is defined as this guy, something that doesn't change along the streamline when the process is isentropic. Okay. So we can do something similar to this. So when we do to this, the only thing that's changed is there is this additional gamma over here that gets multiplied on the left hand side. Okay. So how you would derive from the pressure is going to be something very similar. So if you derive pressure, you're going to see the pressure times 1 plus gamma minus 1 over 2 m squared to the power of gamma over gamma minus 1, because this instead of 1 over gamma minus 1, I get gamma over gamma minus 1 here. So that is going to be proportional to a constant, and that's defined as total pressure or stagnation pressure. Okay. Now the stagnation pressure, actually we can say something about it. When the Mach number is very small, anybody remember the Taylor series expansion for 1 plus epsilon to the power of something?
P plus dynamic pressure.
No. Yeah, that's what I'm deriving. But like, I'm just asking, does anybody remember 1 plus epsilon to the a when epsilon is very small? What is the... Exactly, that's 1 plus a epsilon plus o epsilon squared, right? So that's what we are going to be using here. So if Mach number is very small, this guy is equal to whatever the power is equal to 1 plus this guy times this guy, right? Okay, and this guy times this guy, the gamma minus 1 cancels out. What you end up getting is 1 plus gamma over 2 times m squared. Alright? And that you can just derive, if you look at the difference between stagnation pressure in this definition and the static pressure, you're going to get exactly half rho u squared. Okay? I can do the derivation for you. So at Mach very, very small, pt minus p would be equal to p times half gamma m squared. Okay? And m squared by the definition is going to be u squared divided by gamma p over rho, right? So I have gamma over 2 here. And the gamma cancels out, p cancels out, I get half of rho u squared, right? So that's the same as our incompressible relationship of how basically stagnation pressure is equal to the static pressure plus half rho u squared. That's basically Bernoulli's, right? And what we derived over here is a generalization of Bernoulli's law in compressible flow. So in Bernoulli's law, it basically says along the streamline, the stagnation pressure defined as P plus this guy, which is PT, doesn't change. In compressible flow, Bernoulli's law is exactly the same. It says PT, the total pressure, doesn't change along the streamline. But the definition is different. It's not different, it's extended in the sense that this new definition, the more complex definition, agrees with the original definition, P plus half rho u squared, at very low Mach number. But this new formulation is actually appropriate for any Mach number you want. Alright, any questions on this? highly recommend you try to derive it yourself at home. And that's why there is no homework this week. All right. Okay. So now we can apply this relationship to convergent divergent nozzle. But before we apply this relationship to convergent divergent nozzle, we need one thing more that's going to be derived using exactly the same kind of a logic, using fractional sensitivity. So that is how now we related the Mach number. Let me just copy the stuff here. So Mach number is equal to 1 plus gamma minus 1 over 2 m squared times delta u over u, right? And we remember how does delta rho u over rho u, the fractional sensitivity of the mass flow per unit area, changes as a function of u, and that is 1 minus m squared times delta u over u. Right, again, that's something we derived the first day we look at compressible flow. That is, at low Mach numbers, the mass flow has the same kind of increase as velocity increase. But at Mach 1, velocity increases, there is no change in mass flow per unit area. And at supersonic speed, if you increase in speed, counterintuitively, you have a decrease in the mass flow per unit area, right? That's something we also derived the first day. Now, if you plug that in, what we get is, actually, I'll just write it like this, divided by 1 minus m squared times delta rho u over rho u, right? Okay, and from this, you can actually integrate and see how does rho u, so, this guy can be written as delta of log of rho u, right? And if you divide this all the way to here, what you're going to get is equal to 1 minus m squared. 1 plus gamma minus 1 over 2 m squared times m over delta m. Right? Okay. So here you can start to integrate and see how does rho u change with Mach number. So basically the mass flow per unit area, how does that change with Mach number? So let me go to Desmos and do the integration for you. This integral is, there is actually an analytical solution, but it's a little bit too complicated to actually just do in class. So I'm just going to use Desmos and integrate it for you. How about that? Okay, so the integral here, so this integral is actually going to get to something infinity because as m goes to 0, right, this is going to be, this is going to integrate all the way to infinity. So instead of integrating start from m equal to 0, I'm going to start integrating from m equal to 1. So 1 to x, 1 minus m squared, just do it here, divided by 1 plus 0.2 m squared. So 0.2 is because gamma minus 1 over 2 is 0.2. Okay? And 1 over m dm. So this is the integral. This is what log of rho u changes as a function of Mach number. And of course there is a constant, additive constant. So when I take the exponential, if I take the exponential, the additive constant becomes a multiplicative constant, right? So essentially, this is the mass flow per unit area of a compressible flow. How does it depend on the Mach number? So at a small Mach number, we get a linear relationship. So as Mach number increases, the mass flow per area increases linearly. But that relation starts to become almost a flat at Mach equal to 1. At Mach equal to 1, I get the maximum possible mass flow per area, rho u. And beyond Mach 1, I get a decrease. Okay? So which means if we draw a convergent divergent nozzle, and if the whole process is isentropic, there is no shock waves, Then the area, so this is mass flow per unit area, so maybe say f of x is equal to this. The area of a convergent divergent nozzle is equal to 1 divided by f of x. Let's visualize it a little bit better by this, and let me just yeah, so that's how a convergent divergent nozzle would look like if the Mach number is basically 0, 0.2, 0.4, 0.6, 0.8, 1, 1.2. So if the Mach number increases linearly as a function of x, this is exactly how a convergent divergent nozzle would have to look like. Okay, and for any shape, if I have an arbitrary convergent divergent nozzle, you can basically look up the area of that nozzle, map it, assuming the same throat area. So this is the throat area, right? Assuming the same throat area for any shape, the nozzle, you can map the area to here and find out what Mach number at that particular section is. All right. Questions? Okay. And once you find out what Mach number is, you can then use the relation we just derived in the previous slide to find out what is the ratio of the density with respect to the stagnation density, which is the upstream density when the Mach number is 0, and also what is the pressure, right, from the stagnation pressure, which is the pressure upstream at Mach equal to 0. So by that way, you can solve any convergent divergent nozzle problems. Okay, any questions? All right. I know I'm going faster over here, so don't feel free to ask questions. Like if I don't want to be losing everybody. You have a question? No? You too confused to ask any questions? Or I mean, feel free to interrupt me, and if there is anything I'm not explaining clearly. So basically, the process to solve convergent divergent nozzle is basically you go from the area to Mach number, and you go from Mach number to pressure, density, everything, right? So this is how these plots are generated. Okay, so for there are actually two different scenarios in convergent divergent nozzles. One scenario is when at the throat, the Mach number has not reached 1 yet. Right? So in this kind of a scenario, the whole flow is subsonic, and you can determine various things. For example, if you know the pressure of the outlet and the stagnation pressure of the inlet, then you can compute the pressure ratio P over PT, right? From P over PT, you can compute P over PT is basically this guy reciprocal, okay? And from there, you can compute the Mach number at the outlet, all right? So once you can compute the Mach number at the outlet, you can compute what is the mass flow per unit area at the outlet, right? Okay, so because the mass flow per unit area, so once you have the Mach number, you can not only okay, so from the pressure, you know the Mach number. From the Mach number, you know the density, because usually you are given the upstream conditions, right? You know what is the atmosphere condition from upstream. So from Mach number, you can also compute the density, because you know stagnation density, you know the Mach numbers, you know the actual static density. You know density and pressure, which means you know the speed of sound, and you know the Mach number, which means you know the velocity, right? Okay, so knowing velocity and density, you know the mass flow over here. Once you know the mass flow over here, you know the mass flow through the entire nozzle, right? Because it's a steady state. All right. Okay. And for example, if somebody asks you what is the Mach number at the throat, You can figure that out by taking the mass flow over here. From the ratio of the areas, you know the mass flow per unit area here. And from the mass flow per unit area, you can figure out the Mach number, because that's exactly the plot we have here, right? You know the entire thing is subsonic, so you are looking at this branch. If you know the mass flow per unit area is this, then you know the Mach number. Yes?
Can you explain again why the ratio of the outlet in the areas gives you the...
Oh yeah. Why does the ratio of the the ratio of the...
You said right now you take the area of the outlet, the ratio is...
Yes. Okay. So let me maybe write it down. So for example, if you know P over PT, right? You know the pressure ratio. That gives you the, let's say this is the outlet. That gives you the Mach number at the outlet, right? And together with the rho T, this together with rho T gives you rho, right? And now you have okay. So let me just say if you have both P outlet and if you have why can't I erase this? If you have both P outlet and the PT outlet, you have this. And now if you have P outlet and this is basically rho outlet, then you're going to have the speed of sound at outlet, right? And from the Mach number and the speed of sound, you can have velocity at the outlet. And now you have a rho and you have velocity that gives you rho u outlet, right? Okay. And then if you also know the area of the outlet, you are going to know what is the rho UA, not just at the outlet, but throughout the entire nozzle, because of mass conservation. This is the same throughout the nozzle. And then if you know the area of the throat, right, that gives you rho U at the throat. Let me just say star. Okay, and from rho U of the star, you look up this table or plot, you know the Mach number at the throat. Is it? Oh, looks complicated, but like this is essentially from one quantity, right? From the basically the okay. So from the upstream, so usually you know the upstream quantities, and given one quantity at the outlet, you can figure out everything that happens at the nozzle. All right. So this is assuming a subsonic nozzle. So how do you find out if the nozzle is subsonic or not?
Check if the Mach number is 1 at this road.
Check if this number, rho u, is below or above the maximum possible. Okay, so whenever you compute a rho u, mass flow per area, that is actually lower, because this actually gets the maximum mass flow per area because it's the minimum area, right? So if this one has a lower than maximum mass flow per area, then the entire nozzle is going to be operating over here. There is no way the nozzle can operate over here. Do you agree? So the whole thing is subsonic. But if through that calculation assumes everything is isentropic, which means no shockwaves. By that calculation, if you calculate a mass flow per area that is this, that means it's impossible. Okay? That means two things. One thing is that the nozzle is not going to operate solely on this region. And the two is the flow is not isentropic somewhere. Yes?
So would we use like the jump conditions? Or?
Then there will be shockwaves. That's what I want to talk about for the remaining of the lecture. Okay. All right. So this is the subsequent cases. So for all not purely subsonic cases, the throat is choked, which means the throat is at Mach 1. Okay? Everything happens upstream will be exactly the same. As long as the throat reaches Mach 1, the conversion part of the nozzle doesn't change anymore. No matter how you change the downstream pressure, nothing changes upstream of the throat. Okay? And the one way you can think about this is because there is going to be a supersonic region sitting somewhere over here. The flow becomes Mach 1 and now it's supersonic, right? A supersonic flow, information only propagates downstream. Information cannot propagate upstream. So no matter how you change the condition downstream over here, it cannot go through this supersonic region. And whatever is upstream of the throat, it has no way of knowing even the condition has changed the downstream. Okay, so now if you further decrease the downstream pressure over here all the way to this point, what actually happens is the supersonic region expands, and the shock wave is where the flow transition back to a subsonic flow would keep moving more and more downstream. Okay, so let's now discuss what's happening over the shock wave. So the shock wave, first of all, we have to understand is not isentropic. Why is that? It's because the shock wave is very thin. So if you ignore viscosity, you are actually going to derive a shock wave that's infinitely thin, zero thickness. But in reality, that's not what happens. In reality, there is molecular motion. So the motion of the molecules, the average speed of the molecules is actually faster than speed of sound, actually several times faster. So the molecules actually moves across shock waves. Okay, and the diffusion. Because of the shock wave, on one side is supersonic, the other side is subsonic. There is a huge speed difference. So the average speed of the molecules are different. So molecules crossing the shock wave transfers momentum through viscosity, and anything that involves a significant viscosity is not going to be isentropic. Let me just go through this to a shock. And okay, so how do you derive? So what happens across a shock? Let's just look at the shock over here. We have m left greater than 1, and it suddenly transitions into m right less than 1. Okay. If you look at the control volume, that's very, very thin, that spans across the shock wave. And let's just assume the area, upstream and downstream area of the control volume is equal to 1, just to make things easier. The first thing we want to know is that rho L times UL has to equal to rho R times UR. That's simply a mass conservation, right? The velocity across the shock wave decreased, the density has to increase. Because otherwise, this very thin layer, there is no way for the mass to accumulate or decrease inside. Right? Okay, so let's just denote that as m dot over the shock wave. It doesn't matter left or right, it's the same quantity. Second thing to notice is that momentum also has to conserve over the control volume. So what is the momentum flux into the left? It's rho L times UL squared, right? Or you can write it as m dot times UL. M dot is how much mass flows through per unit volume, and the UL is how much momentum there is per mass, right? That has to equal to rho R times UR squared, or m dot times UR. Well, this is actually not true, because there is also a force on the control volume. What is the force? Pressure, exactly. Okay, and the pressure is basically we have to add the PL and add the PR onto this to actually have the momentum conservation equations. Now, as we cross the shock, right, velocity decreases. So m dot is the same, but UL is slower than UR, which means how does the pressure change? UL is higher, UR is lower. So the pressure has to, PR has to rise compared to PL, right? So across the shock, density increases, pressure increases, but not isentropically. Like you cannot follow like P is equal to rho to the gamma power, because that's isentropic relationship. It doesn't work over here. Although qualitatively the relation is the same, density increases, pressure increases, but quantitatively the isentropic relation is wrong. Alright, okay, so from this you can actually divide both sides by m dot, because it's the same. You get UL plus PL over m dot is equal to UR plus PR over the same m dot. And I don't think I have time to write the whole thing, but like you can represent another thing I think that you have to use for shock relationship is conservation of energy. Okay, so conservation of energy, basically, it's the easiest thing to visualize this is imagine this is actually happening in the convergent divergent nozzle. And the convergent divergent nozzle has both the inlet and outlet much larger than the shock area, so that the flow is basically Mach 0 downstream and also basically Mach 0 upstream on both sides. Okay, so through that, and if you write out the conservation of energy equation, you are going to find out that the temperature at the inlet and the temperature at the outlet will be exactly the same. The pressure is going to be dropped. I mean, the pressure actually at the outlet, because of the existence of the shock wave, is going to be lower than the pressure at the inlet. But temperature is actually exactly the same. Okay, so that means stagnation temperature, or TT. Oh, I think I didn't write down the temperature relationship over here, but the temperature relationship can be just derived from this and this, right? So because pressure is going to equal to rho RT. So T is going to be equal to P divided by rho divided by R, which is a constant. So through the division, you are going to find out the stagnation temperature can be defined as temperature times 1 plus gamma minus 1 over 2m squared. After the division, we have this minus this, which is gamma minus 1 both on the denominator and on the numerator. So this power is actually equal to 1. So the temperature, so the total temperature can be defined as the temperature to the times this quantity, which appears everywhere, right? I mean, this quantity is basically just a fractional sensitivity of Mach number to velocity that appears in a lot of places. Okay, so the total temperature actually also doesn't change. And you can actually write the velocity in terms of Mach number and total temperature, right? Because for example, velocity is equal to Mach number times square root of rho square root of not rho RT, gamma RT, right? So that's basically speed of sound, and the T can be written as gamma RTT times 1 plus this m squared to the power of minus 1, right? That's the static temperature. So basically, you can. It turns out you can write both the left and right in terms of something proportional to stagnation, square root of stagnation temperature, and just the Mach number. And through this equation and the mass conservation equation, which gives you that m dot is the same, and the stagnation temperature is conserved, you can basically derive the relationship. You can have this equation on both left and right written as a function of Mach numbers, written as a function of the two Mach numbers. So this equation actually gives you the relation between the Mach number upstream and the Mach number downstream. If you plot it, if you plot m2, which is the Mach number downstream, as a function of m1, which is the Mach number, which is the supersonic Mach number upstream, you get a relation like that. So essentially, as Mach number increases further than 1, the downstream Mach number decreases lower and lower. Okay. And so this portion, when the both upstream and downstream Mach number is close to 1, we call this a weak shock. And when the upstream Mach number is much higher than 1, which also means the downstream Mach number is much lower than 1, we call it a strong shock. Okay. So the strength of the shock is basically determined by a single number. What is the Mach number upstream? And when I say Mach number upstream, I'm looking at a frame of reference in which the shock wave itself does not move. Right? Like all these conservation equations we are using to derive these are steady state. A steady state control volume around this. I mean, if the shock wave moves here and here, then this conservation may not be true anymore, right? Because then there is a change in how much momentum there is in the control volume. Okay. What else? So now you have the Mach number ratios. We can just plug the Mach numbers into the equations that determines the density ratios, the pressure ratios, and you would also get a density ratio and pressure ratio like that. Okay, so here you can basically use these equations to solve pretty much all the problems relating to shock waves. Let me just give you one example. So I don't think I have time to work through this example, but like I would give you the basic idea of how to solve problems like that. So a rocket, let's say, explodes during a ground test, which hopefully didn't kill anybody, but like it sends a shockwave traveling from the explosion into ambient air with a given temperature and a given pressure, right? So when the shockwave reaches you, hopefully it's weak enough. But you still feel a sudden pressure increase of 50,000 pascals. Now, what does that tell you about the shock wave? It tells you, okay, so is this 100,000 pascals upstream or downstream of the shock wave? Remember, it's still ambient air, okay?
By downstream, you mean before the shock wave?
By downstream, I mean with the frame of reference that moves with the shock wave. Okay, it's the downstream flow of the shock wave. So imagine a shock wave. That's the rocket. A shock wave comes by from that way, right? If you take the frame of reference that travels with the shock wave, is the ambient air upstream or downstream? Upstream, exactly. Okay, and is the air closer to the rocket? Upstream or downstream? It's downstream, right? Like if you're traveling with the shock wave, then the air is moving towards that rocket that just exploded. Okay, so now you know the ratio of pressure upstream and downstream of the shock wave, right? The pressure downstream is always higher, which means the downstream is 150 pascals. The pressure upstream is 100. So you know the pressure ratio. If you know the pressure ratio, you can work out the Mach number, right? And that's the Mach number of the flow upstream, m1. Now, how does that Mach number relate to the speed of the shock?
We have the temperature, we can find the...
No, it's easier than that. So,
The equation we talked about.
well, that's the, okay, so these two Mach numbers are both Mach numbers of the flow relative to the shock. Now I'm asking, what is the speed of the shock? Yes?
You know the temperature of the air.
I know the temperature of the air.
Mach number.
I know the Mach
You know
number.
the speed of sound in the air.
I know the speed of sound upstream of the shock, right, in the ambient air. Okay? Now,
Velocity over.
that's right, but the key here is that the speed of the shock relative to the ground is exactly the speed of air upstream of the shock relative to the shock. Does that make sense? Because the air before the shock arrives is stationary, right? Okay, if the shock wave is coming towards the stationary air, if you take a frame of reference that travels with the shock, then the stationary air is going towards the shock at the same speed as the speed of the shock relative to the ground. So you just need to figure out the speed of the shock, you just need to figure out what is the speed of the upstream air relative to the shock, which is exactly what you said, right? You know what is the upstream temperature, you figure out the speed of sound, and from the pressure ratio you figure out the Mach number, you get the speed. Okay, so that's how you figure out if you are sitting here, you suddenly feel a pressure rise of 50,000 pascals, which is probably going to blow you backwards. Okay, you know how fast is the shock wave coming in that blew you backwards. Alright? Okay, so see you on Friday with Professor Harris giving the lecture.